Welcome to section 2.5. Really the big topic in this section is countable additivity, but we've already dealt with that. We stated that in section 2.3 and we proved it in section 2.3. I'm unclear on why the book's chosen to hold countable additivity until section 2.5, but we've processed it. So we'll look at a couple other things from this section. In particular, we finally defined Lebesgue measure. We haven't formally done that in the notes. I've verbally probably done it several times. And we'll look at a couple of properties of Lebesgue measure. And Lebesgue measure will be defined on the sigma algebra of Lebesgue measurable sets. That sigma algebra we dealt with in section 2.3. And it's not defined on the power set of the reals. So non-measurable sets do exist. More details on that in the next section, section 2.6, I believe it is. Okay, so to formally define Lebesgue measure, if we take outer measure, M star, and restrict it to calligraphy M, the sigma algebra of Lebesgue measurable sets, that's what Lebesgue measure is. We'll denote it without the little asterisk and simply denote it as M. Okay, not all sets are measurable, so from here on out, every time we talk about measure, we'll have to make the comment that we're restricting this conversation to the sigma algebra of Lebesgue measurable sets, because we're talking from here on out in the beginning of the book, part 1 of the book at least, we're talking about exclusively Lebesgue measure. What we know about Lebesgue measure, we've said this stuff before, but now we can say it in terms of Lebesgue measure M instead of outer measure and measurable sets. The set function Lebesgue measure defined on this calligraphy M assigns length to any interval. The measure of an interval is its length, is translation invariant because M star is translation invariant on everything, and is countably additive. We established the countable additivity, like I said, in section 2.3. So one last time, we wanted 4 things. These are 3 of them. The 4th one we wanted was that the measure we introduced be defined on the power set of the reals. The measure be defined on every subset of real numbers. And in order to get these, in particular, the countable additivity, we had to back off of that 4th desire that we have a measure on the power set of the reals. And we have to settle for a measure defined on a sigma algebra. It contains the Borel sets in particular, and I kind of dare you to think of a set that's not measurable. We'll construct one using the axiom of choice in the next section. It's quite exotic, but we don't have a measure that's defined on the power set of the reals. So that's our setting. We're about to show measure is continuous in a sense. To inspire why this is called continuity, let's recall a function of a real variable defined appropriately is continuous at a point x sub 0 in its domain if the limit as x approaches x sub 0 of f is f of x sub 0. You can evaluate limits by substitution when you're dealing with continuous functions. More suggestively, the limit as x approaches x sub 0 of f of x equals f of the limit as x approaches 0, a little typo there, of x. So you can take the limit inside the function. The limit goes inside the function. I still need the argument x there. And of course, as x approaches x sub 0 of x, that is x sub 0. So you can evaluate limits by substitution, but I want to view it as limits go inside continuous functions. So when dealing with continuous functions, we can pass limits in and out of those functions. I bring that up because the title of the next theorem is measure is continuous, and we need to deal, since measure is defined on sets, we need to deal with a limit of a sequence of sets. And that's defined provided we have either an ascending or a descending sequence of sets as follows. If a sub k k equals 1 to infinity is an ascending collection of measurable sets. That is, A1 is a subset of A2, is a subset of A3, and so forth. In general, the sets are getting bigger, air quote bigger, because, well, I'm not making a claim about their cardinalities or necessarily their measures, but a claim in terms of set inclusion, specifically this IE statement. So the sets are containing more stuff, potentially. In such a collection of sets, if we take the union from k equals 1 to infinity, a sub k, that is, by definition, that's the limit as k approaches infinity of a sub k, depending on your background, probably from senior level analysis. I don't think this was explicitly mentioned in any of our background material. It's somewhere in chapter 1 of the Royden and Fitzpatrick book. But this is how you define a limit of a sequence of sets. You can't take a limit of just any old sequence of sets. We need them nested in this sense to consider a limit in terms of a union. So the claim here is the measure, so it's a measure claim, the measure of the union of all of these sets a sub k, that is the measure of the limit as k approaches infinity of the a sub k sets, because that limit is by definition this union for an ascending collection of sets. The claim is that equals the limit as k approaches infinity of the measure of a sub k. We've got the limit inside the measure function there and outside there. That's exactly what continuity of a function is. So that's the reason this is called measure is continuous. So we brought the limit outside of the measure function. The equality here, that's just substitution. This union is the limit as k approaches infinity of a sub k by definition. If we had a descending collection of sets, say b sub k, so b sub k contains b sub k plus 1. So descending, the sets are getting, air quotes, smaller. We get a subset inclusion more specifically. And the measure of the first one of these sets is finite. So the measure of all of these sets is finite. Monotonicity will give you that. But here is a bit of extra hypothesis we didn't have above. Claim is the measure of the intersection. We were doing unions in the first one. The measure of the intersection from k equals 1 to infinity of b sub k. That is, by definition, the limit as k approaches infinity of b sub k. So again, it's a definition that gets us from here to here. That's just a substitution, the meaning of the limit of a sequence of descending sets, descending in this sense. And the claim is you can bring the limit outside the measure function again. So the measure of the limit is the limit of the measures, is the claim in both of those. Quick observation before we look at the proof. The fact that we added this is necessary. In problem 2.25, you're to show that without the assumption of finiteness of that in measure of that first set, the result doesn't hold. So let's look at a proof. And keep our eye on where we use this finiteness hypothesis, if I recall at the time. Okay. So let's prove both parts of this. First, let's deal with the ascending sequence of sets. If the measure of any of these a sub k's, say a sub k sub 0, if the measure of any of those a sub k's equals infinity, some k sub 0, then it's a trivial result. Over here, if any of the a sub k's has infinite measure, then the measure of the union, this will be infinite. The sets are ascending. So if we have one that has measure infinity, then all the ones following it in the list also have infinite measure. It's monotonicity again, if you like. So anyhow, we get infinity out here and we get infinity out on this side as well. So without loss of generality, we can assume the measure of a sub k is finite for all k. Not like the situation in the second part. Here, well, it still holds if we get a set of infinite measure. It just holds trivially, in fact. But we've taken care of that case. So without loss of generality, suppose all these sets have finite measure. Okay, we're going to define a collection of disjoint sets because we're talking Lebesgue measure. And one of the powerful properties of Lebesgue measure, because we went to great lengths to get it, is countable additivity. So define A sub 0 to be an empty set and define C sub k to be A sub k set minus A sub k minus 1. This is an ascending collection of sets. So I kind of think of the sets as getting bigger. They're nested in a sense, and we have this subset inclusion. So there's maybe some stuff in A sub k plus 1 that's not in set A sub k. Think about adding a little bit more stuff every time. Well, C sub k is defined to be that stuff that's added. It's in terms of A sub k and A sub k minus 1, but C sub k is the stuff in A sub k that's not in the previous set in the list, A sub k minus 1. And we're defining this for k greater than or equal to 1. Well, when k equals 1, we'd need to reference an A sub 0, and that's why we specifically defined A sub 0 to be an empty set over here. So C sub 1 is A sub 1. C sub 2 is A sub 2 minus A sub 1. The stuff that's in A sub 2 that's not in A sub 1, and so forth. The A sub k's are an ascending sequence by hypothesis. So the C sub k's, then, they're disjoint, ascending and nested. The C sub k's are disjoint. C sub 1 contains A sub 1. C sub 2 contains the stuff in A sub 2 that's not in A sub 1. C sub 3 contains the stuff in A sub 3 that's not in A sub 2. And A sub 2 includes A sub 1. It's an ascending sequence. So yes, the C sub k's, so defined, are disjoint. Why are you interested in that? So I can use properties of Lebesgue measure, like countable additivity. So we've got equality between these two sets, and we've done this before when we were dealing with sigma algebras. This kind of thing came up a time or two, where we took a collection of sets and made a disjoint collection of sets at unions to give the same thing. So if we want to measure the union of the A sub k's, that's the same as measuring the union of the C sub k's. Remember the little dot in the union symbol means disjoint union. Not a universal symbol, but not an uncommon symbol as well. It's really useful knowing when things are disjoint here. Tells us when we can use countable additivity. Okay, we got disjoint, measurable sets. Maybe a quick comment. These C sub k's are all measurable sets. Set differences are measurable. This is A sub k intersect A sub k minus 1 complement. We're in a sigma algebra. It's closed under complements. It's closed under intersections. It's closed under set differences. Follows. So by the way, the C sub k's are measurable as well. Something to keep an eye on because not all sets are measurable. But we're doing sigma algebra stuff, and we know the collection of measurable sets form a sigma algebra. Measure of a countable disjoint union is the sum of the measures. That's countable additivity. Proposition 2.6 goes right there to justify that equal sign. Let's see, C sub k was defined to be A sub k set minus A sub k minus 1. So from here to here, that's just substitution. All right, we're trying to show the measure of the union equals the limit of this measure. Here we've got the measure of the union, and we're leaving off writing it as a series of the measures of these things. Continuing. All right, here's the conclusion from the last slide was this little equation here. This is the beginning and the ending of it. The excision property of a measure says the measure of a set difference is the difference of the measures. But that required some finiteness of measure. And we do have finiteness of measure. That's why we looked at the infinite case first, because the excision property requires we have finite measures of one of these. We got finite measures of both of these. We're good. So we can write the measure of this set difference as the difference of the measures. Excision property also required some subset stuff going on. The fact that we have an ascending collection tells you this is a subset of that. So these were all parts of the excision property as stated in a couple of sections ago, maybe 3 sections ago. Lemma 2.4.a, because it was a previous section. So excision property allows us to deal with this. And in part 2, when we assumed something was finite, it was so we could use the excision property. But we've got finiteness here also without loss of generality. So we can write the measure of the union as this series. Okay, now a series is just a limit of a sequence of partial sums. So the sum from k equals 1 to infinity is the limit as n approaches infinity of the sum from k equals 1 to n. All right, so let's write that series in the very definition of how you define a series as a limit of a sequence of partial sums. That's calculus 2 stuff. And notice what happens when we introduce this finite sum, which is the very meaning of the series. Were we to let k range from 1 to n, we're going to have, let's see, k equals 1, we'll have negative m sub 0, negative measure a sub 0 plus the measure of a1 at k equals 2. We'll have negative measure of a1 plus the measure of a2. This is telescoping. So we'd have, for example, the measure of a1 when k equals 1 from this, and negative measure of a1 when k equals 2 on this one. So we get those terms to telescope, to collapse. And summing from 1 to n, you're left with this k equals 1 term and this k equals n term. The first and the last term, all those center terms collapsing in a telescoping style. So that'll leave you with the measure of a sub n minus the measure of a sub 0, telescoping sum. And we still got the limit on the outside. Remember a sub 0 is the empty set, so its measure is 0. So we can drop that. I made a comment about that down below. And then we've got a limit of the measure of a sub n. That's exactly what we claimed. Well, I guess we had k's instead of n's, but that's exactly what the claim was. So we've got the measure of the union, that is the measure of the limit equal to the limit of the measures, replacing the dummy variable n with a k down here to match up with the statement. So there's part 1. Ascending collection of measurable sets yields this passing of a limit in and out of the measure function. Part 2, same thing, limit passing in and out of a measure, but for part 2, descending collection of measurable sets. Okay, so let B sub k be a descending collection of measurable sets nested in this sense, and let the measure of the first one be finite. We'll keep an eye on where we use that. Oh, I already told you. We'll use that at some point with the excision principle. Define, for the proof, d sub k equals b sub 1 minus b sub k. For k, any natural number. Now, the b sub k sets, this was a descending sequence that was given. So the d sub k set is an ascending sequence of sets. I guess a crude way to think about it is you threw in a negative sign in some sense. Yeah, the b sub k's are getting quote unquote smaller and smaller. Okay, so the d sub k's are having less and less stuff subtracted from them. So indeed, the d sub k's form an ascending sequence. That's informally correct. The math could use a little spicing up. At this level, you should be able to see that it is certainly d sub k is an ascending sequence. Why did we introduce this? We were just talking about ascending sequences in part 1. So if we'll apply part 1 to the sequence of sets d sub k, not a question, but we'll unravel what we're dealing with here from this. Then we know the measure of the union of the d sub k's. That would be the measure of the limit of the d sub k's because they form an ascending sequence. We know that limit comes out front. That's exactly the conclusion of part 1, provided you're dealing with an ascending sequence. Now, I want to relate this set difference to some of the unions and intersections. We're going to use De Morgan's laws. De Morgan's laws for relative complements state the following. The union of these d sub k, well, d sub k was defined to be b1 set minus b sub k. Okay, so it's the union of these things. Having a set subtraction is the same as intersecting with a complement. That's what set subtraction means. Here we've got a union of an intersection of complements. De Morgan's laws applied to relative complements, relative to set B1 in this case, tells us that that will yield B1 set minus the intersection of the B sub k's. So we've gone from a union of the complements to an intersection of the sets themselves. If B sub 1 equals a whole real line, this is the De Morgan's law that we stated in the background notes. Theorem 0.1, the very first background thing we did was to state De Morgan's laws. It was stated in terms of unions and intersections of sets and their complements, not their relative complements. So it's not stated in our notes like that. Royd and Fitzpatrick stated De Morgan's laws in terms of relative complements. I think it's on like page 4, so it's really background stuff. But De Morgan's law applied to relative complements will give us this identity. So we've taken the union of the d sub k's and expressed it as b sub 1 set minus the intersection of the b sub k's. Let's call that star star. Equation star allowed us to write the measure of the union as a limit of a measure. So I'll glue those two things together on the finale of the proof. Okay. Excision principle, Lemma 2.4.a, says if we have sets of finite measure, and we do, the first one was finite measure, and the b sub k's, they were descending. Monotonicity tells you if the first one's finite measure, they all finite measure. So we're covered on the excision property. That's why we assume b sub 1 to be finite in measure. The measure of d sub k, this is the definition of d sub k. We're dealing with things finite here. In particular, I guess it's the one that we're subtracting. We need to be finite to avoid an infinity minus infinity, nonsensical term here. We get the measure of the first minus the measure of the second. We're good by the excision principle. This holding for all k, a natural number. Okay, now, star star, the previous slide, last equation, we had established the measure of the union of the d sub k's was the measure of b sub 1 set minus this intersection. Actually, we had the set equality, but taking the measures of those representations of the same set produces this. That was star star. The excision property allows us to say the measure of the set difference is the difference of the measures, provided this one's finite. Well, this is a subset of b sub 1 and it has finite measure. This is finite measure. Monotonicity. We know, some sort of shifting gears here. Now let's use asterisk. We know the measure of the union is the limit of the measures. That's where we use part 1. That was called asterisk, the start equation upstairs. That we got from part 1, part I of this theorem. The measure of d sub k was defined to be b1 minus set minus b sub k. We showed upstairs the measure of d sub k right here is the measure of b1 minus the measure of b sub k. So we're substituting this in for the measure of d sub k inside that limit. Definition of d sub k and the excision principle. Here we're taking a limit of, that's a constant, whatever the measure of b1 is, some number. So the limit of the difference is the difference of the limits. This one exists. We're in the process of establishing that this one not only exists, but takes on the value claimed. But down here, we've got measure B sub k. The B sub k's are descending. This is B bounded below, so the limit must exist. But we're cool on limit of the difference is the difference of the limits. Notice that's constant. Now, I want to compare this with this. Like I said, we bounce around a little bit in this one. So this and this are equal. The measure B sub 1 minus this thing equals the measure B sub 1 minus that thing. The B sub 1s are finite. We can cancel those. Finiteness of B sub 1 again. Get the negative sign out of the way, and we know this quantity equals that quantity. This quantity is the measure of the intersection, and that quantity is the limit of the measures. And that was the second claim. So we can pass limits in and out of measures when dealing with, it's a special setting, when dealing with an ascending sequence of sets or a descending sequence of sets. Continuity of measure. We made the observation that that measure of B1 being finite is necessary, so I want to keep an eye on where we used it. Another, this sounds like a really informal idea, but it's not. Definition is about a property that holds almost everywhere. Let E be a measurable set on everything we do from here on out. We're going to have to restrict our attention to measurable sets. Let E be a measurable set, that is in the sigma algebra of measurable sets, calligraphy M. A property holds almost everywhere on E, that's what we're defining, if there is E sub 0, a subset of E, where the measure of E sub 0 is 0, and the property holds on the relative complement E set minus E sub 0. We may also say the property holds for almost all X in E, so almost everywhere, almost all. What you're doing is you're getting a property. We'll give an example here in the next note of what a property is. This property holds except on a set of measure 0. So maybe it doesn't hold everywhere. We'll have to throw away a set of measure 0, and then it holds everywhere. So that's what almost everywhere means. Now, remember where we're going. We're going for integration. We're going for Lebesgue integration. And it might not surprise you to learn, just as the value of a Riemann integral isn't affected by what happens to the function at a single point. You can take a nice continuous function, redefine it at a single point to some other value, but the integral will be the same. That little single point doesn't weigh anything as far as a Riemann integral is concerned. Hey, guess what? With what we're doing, what happens on a set of measure 0 doesn't affect Riemann integrals. I'm sorry, Lebesgue integrals. So Lebesgue integrals will interact with measure 0 sets the same way Riemann integrals interact with individual points in some informal sense. So the reason we're willing to throw away these sets of measure 0 is we're going for integration, and integrals aren't affected by sets of measure 0. You can take a set of measure 0 and change the function however you want. The Lebesgue integral won't change. So that's the reason this comes up. It does come up a little bit early. I don't think we're going to use this term but once in the Borel-Cantelli theorem to come at the bottom here. But hey, the Riemann-Lebesgue theorem said a bounded function on a closed and bounded set is Riemann integrable if and only if the set of discontinuities of that function has measure 0. So the function is continuous except on that set of measure 0. Well, that's exactly this. So we could restate the Riemann-Lebesgue theorem using this almost everywhere verbiage instead of that set of measure 0 verbiage. So a bounded function f defined on a closed and bounded interval is Riemann integrable on that interval if and only if it is continuous almost everywhere on that interval. So there's an alternate way to deal with the Riemann-Lebesgue theorem. almost everywhere is a very, very common term, as you'll see in our future, a very common term in analysis. So there's an alternative statement to the Riemann-Lebesgue theorem that doesn't appeal to the set of measure zero directly. Hey, almost everywhere, it's indirectly appealing to that set. Next result is called the Borel-Cantelli lemma. It says, let E sub k be a countable collection of measurable sets for which the sum of the measures of those sets is finite. So no constraints on the E sub k. We're not doing ascending or descending. This doesn't deal with that, at least initially. They have to be measurable, of course. So we did say they were measurable, but no constraints in terms of ascending, descending. Constraints of being measurable, we will always have that constraint. We'll always have to say it. And I guess this constraint that the sum of the measures is finite. Statement is, then almost all x belong to, at most, finitely many of the E sub k's. Okay, there's I'd say there's room for confusion in what they're saying. Let's look at the proof and elaborate a little bit on what that part means. The proof is actually fairly quick. It's just one slide. Almost all x belong to, at most, finitely many of the E sub k's. So if we look at the set of x's that belong to infinitely many of the E sub k's, it's a tiny little set. It's small in measure at least. It's measure zero. The set of x's for which x belongs to infinitely many of the E sub k's must have measure zero, is what's being said. First, saying infinitely many isn't saying all. Right? I might have an x that's in every other one and not in all of them, so it's not in every other one, but still in infinitely many. So those types of x values. Also, this doesn't make any sense. Well, suppose it weren't true. Suppose that we had, how would we negate this? The almost all talks about a set of measure zero. We'd negate that by talking about a set of positive measure. So if this were not true, then we would have the x's that belong to infinitely many sets having positive measure. So I'd negate this. Well, that can't be the case. If I had an x that belonged to infinitely many of the sets, what's the measure of that set if it has positive measure? 1/1 jillionth? Well, you're going to get that by monotonicity. You're going to have all of these E sub k's which contain those x's, and there's infinitely many of them, to contain that little positive bit. So you're going to add up that little positive bit an infinite number of times. Well, that's going to diverge. So it isn't as weird and abstract as it sounds. Really, it's simply the fact that if I add the same little positive number to itself an infinite number of times, grain of salt on this, I need to word it in the lingo of series and divergence. But let me be a little informal to make sense out of this. If I got this little bitty bit and it's repeated infinitely many times, that series is going to diverge. There's no negatives here, right, to subtract away things because these measures are non-negative. So it should make sense that, yeah, I couldn't have a big positive measure set or a tiny positive measure set for that matter, which is included in infinitely many of these. That would lead to divergence, right? By saying this, they're really saying we have a convergence situation here. Let's go through the proof. All right. Let's look at the first line and then maybe jump down. By countable subadditivity, the measure of the union from k equals n to infinity, as we started at n, we'll see more of that in the next line, k equals n to infinity of the union, k equals n to infinity of the E sub k's, that's less than or equal to the sum of the measures, k equals n to infinity of the measures of the E sub k's. That's certainly bounded above by this total sum. We started at k equals n instead of k equals 1. The sum from 1 to infinity is finite, so this little piece of it is also finite, or this big piece of it. It's the tail of a convergent series. All right, so subadditivity introduces the less than or equal to. All right, yeah, I can't use additivity because I don't know anything about these being disjoint. Apparently, they're not disjoint. If they were, they would have told us. So there's no additivity, but we're getting the boundedness that we're going to need. All right, we're going to look at the intersection from n equals 1 to infinity of the union from k equals n to infinity of e sub k. This part in square brackets, that's why we brought that up earlier. Let's think about that set. Here's the claim. That set is a set of all points which are in infinitely many e sub k's. We want to show that set has measure 0. There can be points in infinitely many, but that's the set of measure 0 in the almost all statement here. Almost all belong to at most finitely many of the e sub k's. So the measure of the set of x values that belong to infinitely many must be 0. I claim this is the set of points that belong to infinitely many. We'll talk about that. And look what we've shown here. The measure of that set equals less than or equal to equals 0. So we've shown the measure of that set equals 0. So if you believe this statement that this is the points that we're interested in, then yeah, this will be a proof. Let's think about this set a little bit more. All right, so what we're doing is unioning from n to infinity e sub k, and then we're intersecting that collection of sets, we're intersecting those from n equals 1 to infinity. Okay. Think what happens when n equals, when n equals 1. When n equals 1, you're just getting the union of all these sets. When n equals 2, in this union, when n equals 2, you're getting the union of all of the sets except for the first one, e sub 1. When n equals 3, you're getting the union of all of the sets except for the first 2. I'll say that correctly. When k equals 2, we're getting all but the first one. When k equals 3, we're getting all but the first 2, e1 and e2 are excluded when n equals 3. And then we're intersecting those as we go. So if I were to take the intersection, say for n equals 1, n equals 2, and n equals 3, if we were to take the intersections of these unions, we'd get all of the points that occur in that union except those possibly in e sub 1 or e sub 2 or e sub 3. Now, they could be contained in some of the others, but what will be eliminated is those that occur in the first 2 or the first 3 of those sets. So, if I had a point that was contained in only, I'm not sure where to point. If I had an x value that was contained in finitely many of these e sub k's, say it's contained in the first 100, well, some of the first 100. Say the 100th, e sub 100th is the last set that contains some point x. Well, when I take n equals 101, that point will be cut out of this intersection. And that works for any x value that's in finitely many of the sets. So what we're doing is, with the intersection, cutting out the points that are in finitely many of the sets, being left exactly with the points that are in infinitely many of the sets, the e sub k's. Well, that's the thing we want to show has measure 0. The measure of that set is, okay, we've got intersection of this union. All right, taking an intersection, we're creating, we're intersecting more and more. So we're creating a descending collection of sets with this intersection here, indexed by the n here. So the measure of this intersection, blah, 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 is the limit as n approaches infinity of the measure of the sets indexed by n, which is effectively these things here. N is the lower bound, but it's an index on determining that union of sets. So we can use the continuity of measure to say the measure of the intersection is the limit of the measures. All right. Now, subadditivity tells us that we've got less than or equal to, the limit as n approaches infinity, dragging that down. This has measure less than or equal to sum from k equals n to infinity, measure of the e sub k is exactly what we had up there. And you're told the sum from k equals 1 to infinity of n measure of e sub k is finite. Claim is this equals 0 because of that. All right, what's going on there? If I took the sum from 1 to infinity, measure of e sub k, remember what you got here. It looks weird because there's all these sets and measures and stuff floating around. But all this is a series. Actually, it's a series of non-negative terms. Throw away the zeros and it's a positive term series. You know a lot of stuff about positive term series from Calculus 2. So what we've got here is a, well, non-negative term series. These e sub k's could have measure 0 for all I know. I could drop those out and then have a positive term series. But you've got a positive term series that converges. Finite. Positive term series either converge or diverge to infinity. This one doesn't diverge to infinity, all right, so it must converge. What do you know about convergent series from Calculus 2? Maybe Analysis 1 or 2. The tails have to go to 0. So here we're summing from n to infinity. The tail part has to go to 0. This is, I think it's a contrapositive of the test for divergence from Calculus 2. Since this converges, the tail has to go to 0. And that should ring familiar from, if not Calculus 2, then from Analysis. The tail of a convergent positive term series must go to 0. So that's the reason this limit is 0. That's the reason the measure of this set is 0. And that's the reason the points which occur in infinitely many of those e sub k's produce a set, this set here, that has measure 0. That is, almost all x belong to at most finitely many of the e sub k's, because those x that belong to infinitely many form a set with measure 0. Borel-Cantelli. Okay, speaking of Borel-Cantelli, we may use this in passing in the future. It's not going to play a big role. This was an addition to the fourth edition, an addition to the fourth edition of the book. It may pop up in the future, but it won't play a really big role. But it is intuitive if you'll think about what all this stuff means about these finitely many versus infinitely many elements of the e sub k's. And finally, from this section, Royden and Fitzpatrick play up the importance of countable additivity. In the book, the big result in this section was the countable additivity, but I moved it back a couple of sections. I like this quote, so I put it in the notes from page 46. In our forthcoming study of Lebesgue integration, it will be apparent that it is the countable additivity of Lebesgue measure that provides the Lebesgue integral with its decisive advantage over the Riemann integral. We had to have countable additivity. Remember, the big picture is we're trying to come up with a theory of integration that first lets us integrate more stuff, and secondly is a more robust theory of integration, which really means it's got more convergence theorems. You can take limits in and out of Lebesgue integrals more often than you can take limits in and out of Riemann integrals. Riemann integration required uniform convergence of a sequence of functions. We mentioned this back in the early motivation. Lebesgue integrals require significantly less constraining conditions to take limits in and out of integrals. And when we were motivating this, we gave reasons why you would want to take limits in and out of an integral. And that takes care of 2.5. The next section covers non-measurable sets. We'll step aside and I'll record a little video on the axiom of choice and some of the history of the axiom of choice. The result from section 2.6 is totally laid at the feet of the axiom of choice. Without the axiom of choice, we don't get this result. And this is a weird result and can be explained in terms of the Banach-Tarski paradox as something really weird. But these weird results, some people try to read physical meaning into. This ain't anything more than you don't have countable additivity for Lebesgue measure, and you don't have countable additivity for some other kinds of measures. It's one of the consequences of the axiom of choice. The axiom of choice is important for a bunch of stuff. Maybe we'll mention some of the things it's important for as well. But on to the axiom of choice and the existence of a non-measurable set next. Have a nice day.